Hello, everybody, and welcome to our last video in Unit 9 and maybe overall for AP Chemistry, which is very exciting for you. Yeah, we're just gonna wrap it up here with applications of thermo, and I think this video would be is gonna be kind of easy for you. A couple different equations, but one equation you don't even really have to know. You kind of just have to be able to apply it. And the last one has an equation, but honestly, I kind of like to use stoichiometry because, I'm a stoichiometry gal at heart. So but I'll show you the equation anyway because you sort of have to know how to work the equation. Anyway, I'm rambling too much. Let's get started. So cell potential and free energy. So we've already related free energy to the equilibrium constant, okay? And with that equation, we looked at, I didn't even get my draw function up here, but we looked at the fact that the delta G for a reaction is equal to negative RT ln K. All right. So the Gibbs free energy and the equilibrium constant have a relationship. And this makes sense because if you have a very large value for K, that means that we favor the products of the reaction. We have a very high concentration of products. This means that my delta G, my Gibbs free energy, is going to be negative because this reaction tends to proceed in the forward direction. So there is a relationship between delta G and the equilibrium constant K. There is another relationship between free energy and cell potential. So in the last video, we looked at cell potential. So of course, in a voltaic or a galvanic cell, we have to have an oxidation and a reduction reaction. And we can calculate the voltage that's either required or that's produced during that particular process, okay, when that transfer of electrons occurs. And that cell potential, if we have a positive value for cell potential, if I'm producing energy as a result of that reaction, if I'm producing electricity, that must mean that this reaction favors the forward direction. So that also means that free energy must also be negative when I have a positive cell potential. So it's all starting to come together. And this is why this unit I think is so important, is because it really starts to wrap up any loose ends we might have had and how all this stuff is interconnected with one another. Anyway, if a reaction has a positive value for voltage, which we know is favorable, then the Gibbs per free energy, so Gibbs free energy must be negative. And like we said, that makes sense. So if it's favorable, we are going to produce quite a bit of products. Gibbs free energy must be negative. And we can relate the Gibbs free energy to the cell potential. So of course, your Gibbs free energy is your delta G, and your cell potential is this little E naught right here. And E naught tends to be units of volts, okay? However, and this is where this kind of stuff starts to throw you for a loop, is we really got to watch units here, okay? And the unit for a volt is actually a derived unit, which means it's a combination of two units. But units for volts are joules per coulomb. Okay, so this is a joule per coulomb. And this is probably going to help us as we progress through doing some reactions together. N is the number of moles of electrons. So if I, for example, am looking at copper plus 2, and if I am adding 2 electrons to make elemental copper, N would be equal to 2 in this case, because there's 2 electrons that are being transferred in that process. F is a new constant, and F is called Faraday's constant. And this value is a little ridiculous, but it's 96,485. And like I said, this is why it starts to get, you have to watch your units. Sorry, I'm pulling out this blue thing here just to double check that all this stuff is on here. And actually the volt thing is on there as well. So this, your blue paper that's given to you, your equation sheet for the exam, has this on it. This is important. And it also has this on it as well. And a coulomb is the SI unit of electric charge. So 1 mole of electrons contains 96,485 coulombs of charge. And we use this as another constant. So this is on your equation sheet. This is on your equation sheet because, like I said, sometimes with units, this comes in handy. And this equation is also on your equation sheet. So we're really knocking off a lot of stuff here. And like we said, if I have a negative value for, or a positive value for my cell potential, a positive voltage, that must mean that my Gibbs free energy must be negative. That's a favorable process. Whereas if I have a negative value for voltage, my Gibbs free energy would be a positive value. That's an unfavorable reaction. And just to kind of talk about what kind of cells would these occur in, favorable reactions tend to occur in voltaic or galvanic cells. These type of cells are ones that produce an electric current. So voltaic or galvanic, they're used interchangeably. Both of those will produce an electric current, so they will have a negative value for Gibbs free energy. On the other hand, if I have a negative value for my cell potential, this would have to be an electrolytic cell. So these reactions can still happen, but remember, I have to put electricity in to those reactions in order for them to occur because they're not favorable otherwise. Let's take a look at this reaction down here, or this sample problem 16. So sample problem 16 says calculate delta G for the reaction below. And we want to determine if this is a favorable process. So we will have to look at those standard reduction potentials on that paper that I gave to you. So it looks like copper is getting reduced and iron is getting oxidized. So if I look at that paper, the process of reduction, so Cu plus 2 electrons yielding copper, produces a voltage of 0.34 volts. So that is a thermodynamically favorable process. Iron, on the other hand, is getting oxidized. So if I look at the standard reduction potentials, I have to keep in mind that I have to flip that reaction around. So elemental iron becomes iron with a plus 2 charge and loses those 2 electrons. If I flip that reaction, remember, I also have to flip my voltage. So I have a positive value for voltage here as well. And this should produce a voltage of 0.78. Now, if I look at this, this is a positive voltage. So this alone tells us that this process is favorable. However, it's not just asking us if it's favorable or not. We want to calculate delta G for this reaction. So if I look at my equation up here, the relationship between Gibbs free energy and the cell potential, because this is the cell potential, this value we just calculated, delta G is equal to N. N is the number of electrons. And in this process, we are transferring 2 electrons. So my N is equal to 2 electrons. Right here, or this is rather 2 moles of electrons, technically 2 moles of electrons. Then I have my Faraday's constant. So Faraday's constant is 96,485 coulombs per 1 mole of electrons. So in this case, moles of electrons do in fact cancel. And then if I plug in my cell potential, so I don't have a lot of room here, so I'm going to continue down below. My cell potential is 0.78 volts. But remember, your volts technically has units of joules per coulomb. This is going to help us because Gibbs free energy, we've already established, tends to come in units of joules or kilojoules. So if coulombs is on the top in my Faraday's constant and coulombs is on the bottom of my voltage, I'm left with just units of joules. So if I solve for this, 2 times 96,485 times 0.78, I get a Gibbs free energy that's equal to negative 1.5 times 10 to the 5th joules, which is what we want. Because my voltage is positive, my Gibbs free energy is negative, and that makes sense because, oh, it's negative. I'm sorry, I forgot my own darn negative sign. Negative NFE. Negative NFE. We should have a negative right here. Look at me. Oh, rats ruins everything. Negative right there. Negative NFE. Please write that in there. Oh my God, this is driving me crazy. Negative NFE. I was like, wait a minute. This should be negative. Negative NFE. Woo! How embarrassing. It does have the negative sign on your equation sheet, so we are good. But that makes sense. Positive voltage leads to a negative Gibbs free energy. That's it for that. So pretty simple. Like I said, the only thing you kind of have to watch out for are units. What you might have noticed, however, is that on those standard reduction potentials, that all of those are true for 1 molar solutions and for gases at 1 atmosphere at 25 degrees Celsius, so at a certain pressure and at a certain temperature. So a question that sometimes arises, well, what if these solutions are not at those conditions? What if my solution is not a 1 molar solution? And what if I have a gas that's not at 1 atmosphere and is not at 25 degrees Celsius? Well, that's when we get this scary equation, which you don't actually have to use this equation, which is great. You kind of just have to apply it. And I think it makes sense to just kind of think about it. Anyway, because if we could just think about this value for Q, because remember, Q is the, at some conditions that might not be the equilibrium constant. I keep losing this thing right here. So remember, we're comparing Q versus K. Q is going to tell us whether or not this is at equilibrium or not. Anyway, consider the following reaction. Okay, I have copper plus 2 is reacting with metallic copper to create iron plus 2 and metallic copper. This has a positive value for voltage. This voltage is true if my copper plus 2 solution and my iron plus 2 solution is both 1 molar. So, this guy right here has to be 1 molar solutions. But the question is, what if they're not 1 molar solutions? So what if this reaction contained a 3 molar copper solution and a 0.01 molar iron solution? Let's think about it. So if I consider, all right, for Q, remember Q is the not necessarily at equilibrium. If I look at these concentrations, so products over reactants, okay, my iron plus 2 concentration is 0.01 molar, and my copper plus 2 concentration is 3 molar. What is that going to do? Okay, my concentration of copper is much higher than my concentration of iron. What is that going to do to the voltage? Is it going to increase the voltage? Or is it going to decrease the voltage? Will this reaction proceed more in the forward direction? Or will it proceed more in the reverse direction? Okay. If I take a look at those, I have a much higher concentration of copper. If I have a much higher concentration of copper than I do iron, this reaction has to favor the products. It's going to make a lot more iron in this case. So, or it's going to make a lot more iron too, and metallic copper, I should say. So we're kind of bringing Le Chatelier's principle into this now. When those concentrations of solutions change, we could produce more or less product depending on which concentrations are changing. You only need to know that part. Okay, so if you consider what is the change in concentration? All you have to think about is, okay, if this is 3 and this is 0.01, it's going to go more in that direction, okay? However, in a college level chemistry class, I'm sure you will have to use this Nernst equation. So the Nernst equation will tell you what is the new voltage. Okay, no, you won't have to do this, but I plugged everything in for you here. So if I have the standard cell potential, your standard cell potential is 0.78 volts. I have all of these variables that are plugged in there. So RT over N times coulombs times ln 0.01 over 3. And you'll notice that when this occurs, my cell potential increases. And that makes sense. I could produce a lot more products because that concentration of my reactants is a lot higher. That's all you need to know for the Nernst equation. The Nernst equation is on your equation sheet, but you won't have to actually calculate this. So right here, you don't have to know this. It's good to see because, like I said, if you take chemistry in college, which I'm sure most of you, if not all of you you will have to use the Nernst equation to calculate, well, what is that new cell potential? For us, all you have to know is the cell potential going to go up, or is it going to go down, or is it going to stay the same? And I actually pulled a multiple choice question for us to look at. So it says here, a galvanic cell generates a cell potential of 0.32 volts when operated under standard conditions according to the reaction below. Which of the following pairs of conditions are needed to construct a similar cell that generates the lowest cell potential? The lowest cell potential. So I keep losing this thing. It's driving me crazy. So the lowest cell potential. So if I have a low cell potential, I want it to be lower than this. My reaction should actually favor the reactants. I don't want to produce a lot of products. So, okay, which one of these will favor the reactants? Let's take a look. My concentration of zinc is 0.5, and my concentration of iron plus 2 is 1. So in this case, my concentration of iron plus 2 is higher than my concentration of zinc. So that one can't be true because that's going to favor the forward reaction. Here, I have zinc plus 2 is equal to 1 molar, all right, so that's 1 molar, and iron plus 2 is 2 molar. Okay, well, that can't work. Notice I'm not even reading this second part yet because I just want to know about concentrations. This also can't work because my concentration for the iron solution is greater than the concentration for the zinc solution, so that can't be true. Next two, so I have zinc plus 2. My zinc solution is 2 molar. And my iron solution is 0.5 molar. That works. This is an option. And this last one is also an option because you'll see my zinc solution is 2 molar and my iron solution is 1 molar. So this is also an option. So now I have to compare this part right here. So notice it says Q is less than 1 or Q is greater than 1. Which one of these now, technically Q is equal to products over reactants, okay? So my ln of Q would be equal to my products. So if I look at C, right, the product of this reaction is zinc plus 2. So it's 2.0 over 0.5. And if I look at this, my Q value should be greater than 1, right? Because if I get this, I get some number that's definitely not 1. And the same thing is true for this. I'm going to get a value of 2. Q is greater than 1. This second one says that Q is less than 1. So that can't be true. So your answer is going to be C for this one. Remember, if K is greater than Q, that means that your reaction is going to proceed in the forward direction. But if Q is greater than K, that means that you're going to favor the reverse reaction. Nice little equilibrium review right there. Those are the types of questions you would see for this, okay? Not actually calculating any new cell potential. You kind of just have to use the concentrations and figure out which one of those is true. But notice how we broke that down. We looked at the first part of each choice first, and then we looked at the second part next. 2 more pages, almost done. You did a Pogel on Faraday's law because I wanted you to see this one. Faraday's law tells us, let's get back to the draw thing here. Faraday's law tells us that the amount of a substance produced at each electrode is directly proportional to the amount of charge flowing through the cell. So what does that mean? Okay, this means that if I increase the charge on an electrolytic cell, I'm going to produce more product. That kind of makes sense, okay? Because if there's more electric current flowing through, that electric current's got to go somewhere. It's got to produce more product. This is Faraday's law. So, more time a reaction proceeds, and the higher the voltage, or more voltage, leads to more product. There is an equation for this, okay? And you'll notice these things drive me nuts because look how many units you kind of have to keep aware of. We can calculate current, okay? So if I consider, okay, what is the current that is flowing through a system? That's my unit of I right here. Capital letter I stands for current, and units for current tends to be in amperes. You'll see it usually denoted as a capital letter A. Sometimes you'll see it written as amps. Sometimes you'll see it written as amperes. And we have to remember that an ampere has units of 1 coulomb per 1 second. Okay, 1 coulomb per 1 second. This is important for us to know. And Q is the charge, which is in units of coulombs. As I was doing these, we can use this equation, but I kind of like doing these a lot more just by doing stoichiometry. Although you do have to recognize this right here. So Q is going to be your charge, and charge has to be in units of coulombs. So you have to end up with coulombs at some point, and T is time. Okay, so it's how many coulombs are passing through a given point in time gives me the current. Let's go ahead and try this one. I have one sample problem here because like I said, I kind of just like to use stoichiometry to figure this out. So when an aqueous solution of copper 2 sulfate is electrolyzed, okay, so this is going through some sort of electrolytic cell, copper metal is deposited. If a constant current was passed through for 5 hours, and 404 milligrams of copper metal was deposited, what was the current? So current is going to be my value for I, okay? And I has units of coulombs per second. Now in this case, okay, we are given the time. So I want to know 5 hours. And if you do a little bit of math, okay, 5 hours is equal to 18,000 seconds. So I already have my denominator here, 18,000 seconds. I have to somehow manipulate that 404 milligrams into units of coulombs. So let's go ahead and do that. I have 404 milligrams of copper. Let's convert milligrams to grams first. So there's 1,000 milligrams in 1 gram. What makes sense to convert to next? When in doubt, mole it out. Okay, we're still using that. We're very deep in our chemistry careers and we're still using when in doubt, mole it out. So let's convert this to units of moles. Molar mass of copper is 63.55 grams of copper is equal to 1 mole. Now, this is 1 mole of copper. We're dealing with electrons here. So, because we are dealing with electrons, we have to convert this to moles of electrons. So, if you consider copper 2 sulfate, in this formula, copper's got an oxidation number of +2. If copper has an oxidation number of +2, how many electrons are being transferred to go from copper +2 to just copper? 2 electrons. So 1 mole of copper that gets deposited contains 2 moles of electrons. Oops, 2 moles of electrons. I was writing a little too much there. I'm still not in units of coulombs, but if I remember, 1 mole of coulombs is the amount of charge that corresponds to 1 mole of electrons. That's Faraday's constant. So 1 mole of electrons has a current of 96,485 coulombs. I'm just going to put capital letter C. A lot of things I have to remember, and this guy right here is pretty important. Faraday's constant. Faraday's constant. This is on your blue sheet. This is going to relate your moles of electrons to your current, to your charge. I keep saying current. Current is I. It's amperes. When you solve for this stoichiometry problem, you will get a value of 1,230 coulombs. Plug this guy up here. 1,230 coulombs per every 18,000 seconds gives us 0.0681 amperes or amps. Okay, the current is 0.0681 amps. What I would recommend doing, these I kind of have to think about still, right? It takes me a little bit of time to sit down and figure these out. So what I would recommend you do is to do just that yourself. Look at the I do, we do, you do's for this one. It's one of the very last ones. And check them out, okay? But we have to remember Faraday's constant, and we have to remember the fact that a volt is 1 joule per 1 coulomb. All of that information is going to help us. And remember, these are in fact on your equation sheet. We're done with thermodynamics at this point. So I'm looking at this equation sheet right now. I have reviewed every single thermodynamics and electrochemistry equation that's on there. I do have one more page, and this page is just a free response question that I took from College Board because I wanted you to show you a sample that you might see. So let's do this one real quick, and then we're done. So molten magnesium chloride can be decomposed into its elements if sufficient voltage is applied. So sufficient voltage must be applied in this case. This is telling me something pretty important. This must mean that my voltage must be negative because this is an electrolytic cell. When you're reading this, you got to keep track of the words because some of the words are very important. Using inert electrodes. It doesn't really mean much for us. That just means that the electrodes are not actually reacting. The products of the reaction are liquid mercury at the cathode. So I have liquid mercury here. This is my cathode. And I have chlorine gas at the anode. We could label this if we want. Cathode. And I have anode. So if I remember, reduction occurs at the cathode. So and oxidation occurs at the anode. And I remember the difference literally because anode and oxidation both start with vowels. So this must mean that magnesium is getting reduced and my chlorine is getting oxidized. So reduced means it's gaining electrons. And this guy means it must be losing electrons. A simplified representation of the cell is shown below, right here. The reduction have potentials related to this overall reaction are given in the table below. So there's the cell potentials. First question says draw an arrow diagram, draw an arrow in the diagram, I think that's what it's supposed to say, that shows the direction of electron flow. So we've already established that your chlorine is being oxidized. And if chlorine is being oxidized, it is losing electrons. Magnesium is gaining those electrons. So my electron flow must be going from chlorine to magnesium. Here's the direction of my electron flow. Whatever's losing those electrons has to go to the other one. So I just answered that guy there. Next question is asking, would an applied voltage of 2 volts be sufficient for this reaction to occur? Support your claim with a calculation. So I have to look at this guy right here. We've already established that magnesium is getting reduced, and this is the reduction part, so this guy works out. Second one, this is also getting reduced, but remember, I have to have an oxidation and a reduction. For some reason, they always give us the reduction half potentials, so I do have to switch this second one. So negative 2.37 volts is for the magnesium plus 2 electrons yields magnesium. I'm going to flip this guy, and that flips the voltage. So I have 2 chlorines becoming chlorine, diatomic chlorine, and 2 electrons. If I add these together, I get a voltage of negative 3.73. This must mean that in order for this reaction to occur, I have to apply at least 3.73 volts of electricity. I have to apply that much. And the question is asking, is 2 volts enough? Well, the answer is no, because we just found that I have to apply almost double the voltage. So we're going to say no, because negative, or we'll say 3.73 volts is greater than 2.0 volts. And that's really all you have to say for something like this. You don't have to go into a major explanation, okay? Because you have to apply 3.73 volts instead. Let's take a look at C. C says if the current of the cell is kept at a constant 5 amps, how many seconds does it take to produce 2 grams of magnesium at the cathode? So remember, we have our equation for current is I equals Q over T. And I have my current. My current is 5 amps. And I want to know how many seconds is this going to take? So T is going to be my variable. What I need to find, though, is what is that charge that's associated with 2 grams of magnesium. So I got to do a little bit of stoichiometry again. So 2 grams of magnesium, molar mass of magnesium, 24.31 grams to 1 mole. This is magnesium, 1 mole of magnesium. How many electrons is it gaining? Well, it's gaining 2 electrons in this process. So 1 mole of magnesium is gaining 2 moles of electrons. And we know to find the charge of this, Faraday's constant, 1 mole of electrons has a charge of 96,485 coulombs. I'm just going to put cool right there. That gives us a value of 15,876 coulombs. Plug this in up here, 15,876 coulombs. And if you solve for this correctly, you should get a time of 3180 seconds. These take practice. I know we're at the end, but you got to take a little bit of time. Try some of those I do, we do, you do's. Do these on your own, okay? They're really not that hard. You kind of just have to remember some of these new things, especially that Faraday's constant, like I said. The fact that 1 mole of electrons has a charge of 96,485 coulombs that is on your equation sheet. You're done with AP chemistry. Isn't this exciting? Maybe you're done. we're probably very close to the exam at this point. So you will be done very shortly. If you have any questions on this, let me know. We got to work really hard these next week or two, however much time is left. And we got to do it. We're almost there. There's the big light at the end of the tunnel. The light's getting so much brighter every second that passes. And then you're done with chemistry for your senior year. Maybe you're a junior. You're almost done. Okay. If you have any questions, let me know. Otherwise, I will see you in class because there is no next video. Bye.